Okay, I'll start as people are joining. Welcome to the weekly colloquium series of the C3.ai Digital Transformation Institute. As many of you probably know, we are a consortium of universities and industries headquartered both at Berkeley and Illinois. And our goal is to promote the use of artificial intelligence and machine learning for the betterment of society. We have two more seminars at least, colloquium seminars at least for the rest of the semester. The next one will be by Wei Liu, and then the one after that will be by Kaiyu Guan. We also have a workshop on the digital transformation of the built environment. And this will be on October 26th and 28th. So if you look at our website, you'll find more information about that. If you miss any of our colloquia or workshops, you can always go to our YouTube page, and everything is archived there. So you can go back and look at our all the old events, and any upcoming events will also be archived there. So the talk today will be roughly 50 minutes long, and there will be 10 minutes for questions and answers. You can use the Q&A feature to ask questions. We'll try to answer as many of them as time permits. So the title of the talk today is Resource Allocation Through Machine Learning in Emerging Wireless Networks, 5G and Beyond to 6G. The speaker is a star in the area of the communication networks and machine learning. It's Sanjay Shakkottai, who received his PhD from the Department of Electrical and Computer Engineering at the University of Illinois, Urbana-Champaign in 2002. He is at the University of Texas at Austin, where he is the Cockrell Family Chair in Engineering and a professor in the Department of Electrical and Computer Engineering. He received the NSF Career Award in 2004, was elected an IEEE Fellow in 2014, and very recently he was a co-recipient of a very prestigious Best Paper Award from the IEEE Communication Society, the William R. Bennett Prize, which is an award given to the best paper of multiple journals, actually, not just one journal, selected best paper amongst multiple journals of the Communication Society. His research interests are in are at the intersection of statistical learning, wireless networks, resource allocation, and he works on, he's applied them to wireless networks on online platforms and many other things. Sanjay, take it away. Oh, I just want to mention one other thing, actually. I guess Sanjay is also part of two recent AI institutes. So I think that is part of a theory AI institute and an AI institute focused on the application of AI to communication networks. So I think I'm looking forward to what he has to say about these topics. Go ahead, Sanjay.
Thank you very much, Shrikant, for the kind introduction and for the invitation. So let me just share my screen. Are you able to see my screen?
Yes.
Is it coming through? Awesome. Okay. Thank you so much. So I want to talk about resource allocation through machine learning in emerging wireless networks. But before I start getting into the technical details, I want to talk a little bit about the evolution of the wireless network to 6G. So wireless networks are becoming very important across the board for through society, meaning that the way we are pretty much anything we are doing right now to access the rest of the world is through this wireless edge network. The kinds of devices that are connecting to this, laptops, iPads, mobile phones, what have you. But beyond just these kinds of devices which humans interact with, there's a whole bunch of other devices which are also connecting to this network. For example, if you think of a vehicular network, map download for autonomous driving, or V2X type communications, or in terms of robotics applications, or in terms of camera networks, or more broadly, the Internet of Things, the kinds of devices that are connecting among each other is through this wireless network. And so there's much greater heterogeneity as time is progressing. In terms of deployment scenarios, again, there's a lot of heterogeneity, and increasingly so, from urban to rural to even during time of day, depending on whether it's rush hour or not. And same again with spectrum. both in terms of spectrum characteristics as well as availability. The kinds of frequencies that are available are quite diverse. Their characteristics are diverse. So this is one side of things. The second is increased demand. So not just in terms of throughput, but also you want sub-millisecond latency requirements. So you want for mission critical applications to maybe application specific metrics. If you're talking about video, you don't even have a mathematical characterization maybe of what is good quality, except through some psychometric analysis. So this is heterogeneity, this demand. And lastly, there's increased flux in the network, meaning the following. If you go back 15 years, so the change in terms of the wireless timescales was quite slow. What I mean by this is the following. The basic unit of time you should think of in a cellular wireless network is an order of a millisecond. So resource allocation, meaning spectrum resources to various users, are allocated at this time scale. Now, when a user comes into a base station or is associated with a cell tower, okay, that's colloquially a base. Colloquially, cell tower, more formally associated with the base station. The user is there for typically several minutes duration, which means look at the two time scales. The one time scale is of resource allocation is a millisecond, and the association is order of minutes, which are many, many orders of magnitude more than the resource allocation time scale. So it was reasonable to design wireless networks for essentially a statistically stationary regime, meaning you have a lot of time to basically average different statistical effects in the network, and you can get steady state performance. However, with all these increased heterogeneity and increased the spectrum characteristics, the timescales are shrinking. Users are coming in and out much faster. The footprints of each base station is decreasing because of the characteristic of the frequency. There's much more dense networks, and these users also connecting via multiple and diverse interfaces. As a result of which, we need to stop thinking about sort of steady state behavior and think about transient behavior. The network is always in a transient, and we need to worry about these things. Okay, so these are some of the challenges in the wireless network. Now let's go to what the vision could be of what the 6G network will evolve to. In a brief summary would be that the network would consist of, let me just switch on my pointer, just a second. Yeah, good. So the network would be a distributed one with distributed intelligence at this network edge, where simple AI agents or controllers will learn online and adapt and interact with each other through open interfaces. So to elaborate on that, let's go back to sort of the 1990s when we had this ATM versus the TCP/IP discussion in the internet. So for those of you who remember, there's something called the asynchronous transfer mode, which is an alternate protocol set for how internet could be managed. The view of the ATM was a much more managed, more complex logic, more tightly connected logic, which was coordinated across the entire internet. The other vision was sort of the TCP/IP world, where the logic was much simpler, but didn't make too many assumptions about the rest of the network, would basically probe, figure out what is going on, learn and adapt. And the internet has been widely successful. And the second view which basically took over and dominated the internet, was one of the reasons for this success. Now let's look at the same analogy in the wireless network. If you look at 3G and 4G networks, you can think of it as a very, very highly managed, essentially opaque network where the controls are tightly coupled. Any kind of change is hard, and any kind of introspection in this network, meaning if you want to know what the state of it is actually pretty hard. The big change that's going to happen from 5G as networks evolve towards 6G is exactly in these aspects. That is, one can probe in various parts of the network, which means that there should be open interfaces. You should be able to deploy much simpler controllers, which can fit into some part of the network and adapt online. and change as the scenario, as the situation changes, and can interact with each other to optimize the entire network. So this is a fundamental change in terms of the architecture of the network itself. And I think that's the biggest change going towards 6G. The hope is that this kind of an architecture can manage heterogeneity much better, and can enable scenario-specific network optimization. And I'm going to talk about a couple of small examples of this when I get to the technical parts of the talk. And importantly, can also provide short timescale guarantees instead of just dealing with the stationary regime. So with this high-level introduction, let's get into sort of some details. I want to talk about two particular examples which tie into this vision. What I'm going to talk about can fit into can be thought of as particular AI controllers which learn and adapt in one part of the network. This is not all of 6G. This is simply one controller. For 6G to happen, these kinds of controllers will be there in many parts of the network. They will also need to have the plumbing and this to request information as needed, and they will also need to learn to adapt and work with each other. So I'm not talking about those parts, but that's the vision of where 6G is going to go. Today, I'm going to talk about AI-based agents which adapt, and we can see what kind of performance benefits you have when you have this adaptive algorithms. So the first problem I want to talk about is in the context of network algorithm design, where I want to talk about scheduling through online adaptation to satisfy ultra-low latency requirements. The second thing which I want to talk about is a network operations problem, where I want to enable scenario-specific network deployment. With this background, let's get into the two parts of this talk. The first part is on joint scheduling of ultra-low latency traffic, along with sort of wideband traffic. This joint work with Arjun Anand and Gustavo de Veciana. Yes.
Sometimes your voice fades in and out, so I don't know if it's maybe you could stay close to the mic or something. I'm not sure. Yeah, maybe the movement.
Okay. Let me. Is this any better?
It's good. It's good, but every now and then it fades in and out. Maybe when you move, I don't know if the mic is sort of where the mic is or something.
Okay.
But anyway, yeah.
Just thanks. Let me just move the mic a little closer and see whether that helps. Okay. So this is joint work with Arjun Anand, who's now at Intel Labs, and Gustavo de Veciana, who's my colleague at UT. So if you look at today's sort of emerging network, this is not 6G, this is even 5G, which is emerging right now. There are three types of traffic which you need to deal with in these kinds of networks. One is called enhanced mobile broadband. Essentially, this is what we think of as high throughput data, web browsing, video streaming, file download, things like that. When you think about eMBB or enhanced mobile broadband, the view you should have is not too tight delay requirements, tens of milliseconds, but extremely efficient, meaning high spectral efficiency, meaning that per unit of spectrum, you're using sophisticated modulation coding to get a lot of throughput through, and using wide bands. That's eMBB. The second type is what I'm going to talk about today, ultra-reliable low-latency communication. You want extremely high reliability, very low latency. This is sub-milliseconds. And this is important for mission-critical control, and is actually one of the special features of 5G. The third, which I'm not going to talk very much about today, is the Internet of Things type traffic. Massive machine type communications, which require devices with long battery life, but very, very, very low rates and intermittent connectivity. So today's talk, I'm going to talk about these two aspects. Okay. The enhanced mobile broadband and the ultra-reliable low latency communications. So for those of you who know wireless, this slide is redundant, but just so that everybody is on the same page, the way you want to think about radio resources is the following. X-axis is the time axis, Y-axis is frequency, which is spectrum. You want to allocate resources to various users, spectrum resources to various users. The way you do that is the following. You have something called a slot in time. This is about 5 milliseconds. That's what you should have in your mind when you're thinking about this slot. And along the Y-axis is frequency. and there are various users which want to get access to this. What the resource allocation does, the scheduler does, is at the beginning of this time slot, it looks at what the demands are, and then decides how to share it across various users. In this cartoon, there are 2 users that are getting the share of these of the resources, the channel resources. The way it's going to actually make the decision is quite complex. It depends on how much data is there for each of these users, how the channels look like for each of the users. Something very special in wireless, as opposed to wireline networks, is that the same spectrum can look very, very different for different users. So qualitatively, think of 2 users, one which is out and one who's standing in a wide open area, the other behind a building. You can see that the rate you can send intuitively to the one behind a building is going to be much lower than the other person, than the person who's in the wide open area. And as soon as that person moves away from the footprint of the building, the rates will go up. So it's the rates at which you can transfer to user is time varying and is user dependent. So this makes this resource allocation problem quite complex. But in any case, what the system does is at the beginning of a slot, take your frequency, partition it among various users. Okay, so this is for the broadband data. What has happened recently in 5G is to support this ultra reliable low latency communications. What this means is the following: some data arrives in the middle of a time slot of 5 milliseconds and demands that it needs to get to some user within a fraction of a millisecond. If you look at a 4G network, this is just not possible, because all the packing and resource allocation decisions happened at the beginning of this slot. When this traffic came, it needed to wait till this point before you could figure out where to pack it in the next block. But what 5G systems allow potentially is to actually instantaneously, quote unquote, handle this extra data. And the way it happens is the following. This big slot is chunked into many, many small mini slots, each one of which is basically an eighth of a millisecond. So what you can do is to overlay this traffic, this ultra reliable low latency communication traffic on an ongoing transmission, meaning in some manner, just stripe that in on communication that's already going on. So now there are 2 time scales at which resource allocation is being done. One which is sort of planned at this time scale. It's a very carefully planned process of who gets how the shares are allocated to various users across frequency. But then something comes and just needs to be snuck into the system in some manner. So these are the mini slot time scale. And this happens by quote unquote preemption of a very interesting kind. Basically, this eMBB traffic, this broadband traffic which is going on, is punctured, meaning you just set 0 power for these users for over some parts of the frequency, or you don't even put 0 power, you just overlay and transmit something else on top of what is already going on. It of course messes up these transmissions, but this green part of this red part, which is ultra reliable traffic, is coded strongly enough and has enough power in it that its receivers will get it with high reliability. Of course, it's going to damage all the ongoing transmissions. The goal is, how do you overlay, how do you puncture these things, such the eMBB traffic, such that you cause minimum damage and still manage efficient resource sharing? Hopefully the problem is clear, and this is actually a very important problem in 5G networks. The challenge, of course, as I said, is that when you puncture, the broadband traffic suffers throughput loss, potentially on catastrophic throughput loss. But what you do have is flexibility along the y-axis, meaning the following. Let's look at this particular time slot. There are these 2 eMBB traffics which are already scheduled. Look, this is some ultra low latency traffic that needs to get co-scheduled. You can put it here as in this dark blue stripe, but maybe you can put it all the way down here. Just destroy essentially this eMBB 5 instead of 4, and so on. And if you have multiple broadband traffic, you can decide where to place it along the y-axis, and so as to create minimum damage. And what do I mean by damage? Well, different users have different utilities. This user may have maybe much more rate sensitive than this particular user who's willing to tolerate more damage. So that's one thing. And the second is that channels have different user dependent rates, meaning this particular user may be in a great spot. And so you can, if you transmit to that user, you get a super high rate. This user is located in a poor spot. So the rates are anyway low. So maybe you can just go ahead and damage this person more. So you can see qualitatively, at least, there's a lot of different dimensions along which you can trade things off. To make this concrete, and also for those of the audience who have not sort of thought about wireless scheduling, I thought it may be worthwhile to have a simple thought experiment.
Sanjay, there's a question. I know you said you wanted questions at the end, but you said clarification questions would be good.
Sure.
Venu asked a question. Why not schedule everything in mini slots?
Why not schedule all eMBB and
right.
Okay, it's just too complex because scheduling every 1/8 of a second, you just to chunk up the data is extremely hard. These are large packets. You need then segmentation, reassembly. There's a whole bunch of other things which you need to take care of. If you do it in this level of granularity, you're going to have way more wastage in terms of packaging the data at the link level, and two, at the MAC and the link, and two, that the complexity increases tenfold. Is that, yeah, I guess that's really, so for the reasons of these two, you'd like to have big chunks for eMBB traffic.
Okay.
Okay. So a thought experiment of where do we puncture? So let's now look at the simplest scenario, two eMBB users, okay? Meaning they have the same, so that means completely symmetric. And the channel, the time varying channel for each user is either rate 1 or rate 2. Think of a user either in a good spot or a bad spot, and it's moving around. This is a very simplistic model, and for those of you who have played with wireless, this model is really a toy, but nevertheless, as a thought experiment, this is useful. So if you look at a timeline, basically what you can see is that over time, you can have user 1 having rate 1, user 2 having rate 2, both users having rate 1, both users having rate 2, or user 1 having rate 2 and user 2 having rate 1 over time. So so each one is called a channel state. The channel state basically corresponds to what can you do to user 1, what is the rate you can sustain to user 2. So if you decide you're just going to statically partition and give equal resources to both users, then on an average, over these 4 time slabs, you can see that user 1 will get rate 1 half the time and rate 2 half the time. So on an average, you'll get rate 3 by 2. And similarly for user 2. This is the baseline. Now let's puncture on top of it, and let's do random puncturing. Meaning, I imagine traffic is coming at 50 at every mini slot. Let's say 50% of the resources is required to handle this ultra-low latency traffic. So basically, what's going on is there are lots of stripes. In each one of these tiny stripes, there is some new traffic coming, which demands that they communicate, ongoing communication be punctured. So then, and let's assume that the loss to because of puncturing is linear. Meaning, if I puncture 50% of the communication, then this eMBB traffic will get 50% of the rate. Again, these all we are just looking at one baseline. We'll generalize beyond this very soon. But given this scenario, what happens? Well, if I do random puncturing, essentially each one of these users loses 50% of the rate, and so each one of them will get a rate 3/4. But you can do better. You can do opportunistic puncturing, meaning the following. Given that this is what the situation is, the channel, what you want to do is, whenever user 1 and user 2, whenever user 1's channel is worse than user 2, completely puncture all of user 1. So I lose 100% of it. But on an average, you're giving 50% of the resources to the low latency traffic. When both the channels are identical, 1 and 2, or 1 and 1, well, puncture randomly. And similarly, when user and the symmetric opposite of this scenario between user 1 and user 2 here. What does this mean? This means that I'm selectively puncturing, opportunistically puncturing. And so the rate that user 1 is going to get now is going to be 0 here, is going to be half here, 1 here, and 2 here, which means that on an average, it's going to get 70. So clearly, opportunistic puncturing helps improve over random puncturing. And this is not at all surprising for people who have thought about this particular problem. Now, let's instead do a better scheduling. This whole thing is predicated on, I'm going to just split the channel resources by 2 and do static scheduling among these 2 users. But that's not what you want to do. You want to do opportunistic scheduling, meaning if you look at the eMBB traffic, if you look at this first scenario where user 1's channel was really bad and user 2's was great. So the rate was 1,2. In this case, you want to give the entire channel to user 2. That way you can get rate 2 here and rate 2 here as well for user 2. So instead of drawing a splitting line here, you split here. You give 100% of it. When both are the same, well, split half and half. That's the same here. And here, again, give everything to user 1. So this is classic opportunistic scheduling going back at least 25 years, right? And this kind of scheduling was at the heart of 3G systems. In this case, you can see that the rates, the baseline rates itself are better. You can, because for user, for example, for user 2, it's going to get 4, 1, 2, 0. And if you average that, that's 7 over 4, which is way better than 3 over 2. But now you also see one more interesting thing, at least in the toy example. There's no point doing opportunistic puncturing. Because just random puncturing is good enough. Because anyway, wherever you puncture, at least in the toy example, there is no differential hit to various users. So there is no gain with opportunism here for puncturing. Okay. So the takeaway so far is the following. If you are doing opportunistic scheduling for this, at least this toy example, there is no reason you can do something very simple when in the mini slot. Just randomly puncture the thing without worrying about user state or their requirements or their utilities, and you're still quote unquote optimal. The question is how can you generalize this toy example, and what is the role of learning here? I haven't even talked about any learning here. This is all I've talked about is a particular insight on how to puncture and pack. Okay, so now let's actually talk about the problem itself. There is some I'm not going to go into the details of the notation, but it's worthwhile to sort of look at how you formulate this as a thought experiment. There are a bunch of users. Each user has some utility function. Okay, the ultra low latency traffic, there is no queuing. You just need to immediately schedule it. Now let's look at how you formulate this. Well, you want to maximize the total utility. So there is a sum of the utilities across users. The utility depends on what is the rate that the user gets. So let's think about the rate that the user gets. There are many types of channel states. In this figure, there are 4 channel states. There's a channel state 1, 2, there's a 1, 1, there's a 2, 2, and a 2, 1. In each one of these states, you want to figure out how to partition the entire bandwidth across these 2 eMBB users. That is encoded by this fee. It says what fraction in state S is given to a particular user. Then you want to puncture in a particular mini slot. So that is denoted by gamma. It says what fraction, where is the puncturing happening in a particular state, which user is getting punctured. Okay. Clearly, there are some connections between this phi and gamma, but we'll not get into that. Given a particular splitting and a given puncturing in a particular state, there's a certain throughput that the user gets. That's a function of these pay. Furthermore, there are many states. You need to average across these states to actually get the rate. So the utility to user depends on the rate, and this basically is the parameters you're optimizing is the splitting and the puncturing, which are state and user dependent. The cost function itself depends on various statistics, the state distributions, what are the spectral efficiencies, or what the distribution of how URLLC traffic arrives, and so on. So It's a usual utility maximization problem. There's nothing very surprising here. With these various parameters, the only thing you need to satisfy is some step. Make sure that the amount of puncturing does not overrun the capacity. So there's some normal stability constraints. Okay. If you want to look a little, I've already talked about this, but a little bit more into detail of this formulation. The rate you're going to get, it will depend on the fractions that you've allocated to various eMBB users. It will depend on how much is punctured and what's the model of what happens after puncturing and some averaging over the demands. Okay. This will essentially give you for every state and user some rate, and you need to average this over all possible states to get an average rate. So this is a formulation, and you can solve this. That's not a big deal. But that's not a useful thing from an online for what you want to do in the wireless network. You don't want to solve such an optimization problem every 5 milliseconds. It's just not feasible. So what is surprising is the following. For this system, it turns out that there's a very, very simple linear algorithm, online algorithm, that achieves exactly the same utility as the offline algorithm. And the algorithm is the following. You simply randomly puncture, don't do anything opportunistic. Okay. Once you randomly puncture, for each user, it can estimate the average realized punctured rate. So if you look back in time, the user can estimate what rate it's getting. So that's R bar UFT. Once each user knows its estimated average real punctured rate. So this rate includes puncturing. In the past, some part of it is punctured, as a result of which there's a rate loss, and that's already that's essentially encoded into the R bar. Now, how do you schedule given this? Is the usual gradient-based scheduler. So what's a gradient-based scheduler? If in wireless scheduling, if you didn't have utilities, but you just wanted to stabilize the system, you'd look at the current queue length for a user, you'd look at its spectral efficiency, which means what is the rate you can sustain to that user if that user was scheduled. Look at the product of the two and schedule the largest. The gradient-based scheduler goes back again 20 years. Stoliar's 2002 paper, and essentially generalizes this idea. It says that look at the gradient of the utility evaluated at this rate times the spectral efficiency. So a small minor modification of the gradient-based scheduler, essentially to incorporate this random puncturing and also some iterative allocations. Because there's a large band, you don't want to allocate the whole thing in one shot. You want to do it iteratively, but that's a minor detail. For this and for linear losses, this algorithm achieves exactly the same. It achieves the utility given by this offline optimization problem, which required all these distribution parameters. So something very simple works here. The intuition is essentially the following, which is quite nice. If you do opportunistic scheduling, essentially it operates on the Pareto frontier of the capacity region. And therefore, there is no residual opportunism left for puncturing to extract. With any other type of scheduler which is non-opportunistic, the system is not pushed to the boundary. So there is actually, opportunism is, there's some slack left in the system, and smart puncturing can help improve throughput for everyone. So essentially the takeaway is, as long as you do, so what would you do? You just do smart scheduling at the beginning of this slot using just a gradient-based method and just randomly puncture, and that's actually in fact optimal. And if you go beyond linear losses, so what do you mean by linear losses? So the x-axis, this is the fraction of a eMBB which is punctured. The y-axis is the hurt that happens to that user. Linear essentially means the larger fraction that's punctured, the more is the hurt or the throughput loss. But you could have various other models. You could have a threshold model, for example, meaning up to one point, the coding somehow takes care of it and there's nothing goes bad, and afterwards there's catastrophic loss. I could have a convex model and of how puncturing affects it. In these cases, it's a little more, I'm not going to go into the details, but it's a little more subtle. But again, you need to do some joint allocation, But again, an online, without knowing statistics, you can come up with an online algorithm under which either for threshold or convex loss functions, things are asymptotically optimal and converges the same as the offline problem. So the main takeaway is that, at least for this particular problem of puncturing, a very simple online adaptation for URLLC traffic, which is actually quite important in 5G system, matches the offline optimal algorithm, and you don't need to do some complex design. Okay, so this is one example where online adaptation does help. The second part I want to talk about is on auto tuning. So I want to move to a different time scale where, again, online adaptation seems to help a lot in wireless networks. This is joint work with Isfar Tariq and Rajat Sen, who are students at UT Austin. Rajat is now at Google Research. Gustavo de Veciana, who's my colleague at UT, and Tom, Salam, and Milap, who are researchers at AT&T Labs, and with whom we collaborated on this work. So we are switching tracks, and we are talking about auto tuning. So the problem essentially is the following. In the first part, when I talked about the scheduling, we said that, well, I have some, I want to figure out which users to transmit, and I know what is the rate that the user is going to get. That was implicitly assumed in the first half of the talk. And in fact, this is the implicit assumption whenever we do any wireless scheduling or resource allocation. The way, at least I think about this, is, hey, there are queue lengths for various users. There's a rate vector, meaning if I schedule user 1, then I'm going to get a certain rate. If I schedule user 2, I'm going to get a different rate, and so on. And then now, how do I match queue lengths and rates to actually improve to improve performance? But really, in the wireless network, the feedback you get from the users is signal to interference ratio, SINR, or maybe a channel quality index. And so there is some sort of mapping that maps these channel qualities to the actual rates that can be sustained. In paper, we say, of course, just use Shannon's formula, put it in, you're going to get a rate. So this is not an interesting problem at all. In practice, this is actually a huge problem. So let me talk a little bit about how this actually happens. In practice, say you take a major carrier's network, what you have is something called a CQI to MCS table. This table says, if this is a channel quality, there's a particular modulation encoding scheme that it maps to. This table is essentially what, at the network level, we care about. It says that if user 1 is if you want to transmit to user 1, there's a certain MCS, a modulation encoding scheme that's prescribed. And this table is hardwired. So we want to now question, how is this table constructed, and what if you don't hardwire this table? That's really the objective of the second half of this talk. So to talk about this, we need to let's talk about some of the things I talked about a little more specifically. So suppose you have two users, user 1 and user 2, and they have a certain channel quality. It's put as points in the square as a cartoon. This red point means user 1's channel quality is this point, user 2's channel quality is this. And let's say that intuitively, as you go this way, the quality improves. As you go upwards, the quality improves. So this red point qualitatively means user 1's quality is not great, user 2 quality is great. Similarly, this blue point means that user 1's quality is somewhat better, user 2's quality is worse. And for each one of these points, there's a rate mapping that goes on. Meaning, if you are working with this red point, if you look at the throughputs that user 1 or user 2 can get, it basically is characterized by this capacity region. This basically means the following. If the world currently looks like S1, this red point, in this particular time slot, and you decide to transmit give all the channel resources to user 1, this is the particular rate you're going to get. If you give the entire resources to user 2, this is the rate you're going to get. This is essentially, quote unquote, an instantaneous capacity. And if you decide to co-schedule users then as you can achieve any point along this red boundary. It's not just time sharing. It's usually better than time sharing because of MIMO and more complex physical layer scheduling, physical layer flexibilities. Similarly, for the blue point, which is a different time slot where the channel 1, the users potentially were in different locations, or the channels were in different conditions, what have you. But the the environment looks different and the associated capacity region looks different. So hopefully the problem is, the setting is clear. What is quote unquote assumed, at least by me and many other networking folks who think of scheduling, is this mapping from this square to this figure is known. And so all we worry about when making resource allocation decisions is this figure. When you see a channel state, red, so we know that we are on a red, and then we know the demands for user 1 and user 2, and figure out which point on this curve you should operate on. This is a sort of an oversimplified summary of what scheduling is about. But suppose that but now let's dig into how this map is created. Typically, this map is handcrafted in a laboratory and from many different deployment situations, and then this fixed map is put into every base station. The reality is, because there's so much other part of the interference which is not completely encoded in quote unquote the channel state, what you want to do is to have a conservative map. You want to have a map, this channel state, to the modulation coding scheme, which works in most of the scenarios. You don't want to use some aggressive table. And so once you create this table, a major carrier will basically just use this fixed table everywhere on every base station. And then all the scheduling and everything else goes off this table. Question is, can we learn this map online? And if you do learn this map online, what are the benefits? Can you actually get significant benefits? So what I want to talk about is a bandit approach for doing this. I guess I have about 10 minutes left. So I may not even talk too much about the algorithm, but I want to talk about some results with AT&T. So what if you want to just do naive exploration to learn this? Okay. So what does this mean? Naive exploration essentially means the following. In a typical cellular system, the channel quality is quantized into 16 discrete values. The modulation coding scheme has 28 discrete values. So essentially, for every, so if you have n users, or in this cartoon 2 users, you have 16 times 16, 256 discrete channel qualities, and 28 times 28 modulation coding schemes. So what you could do is exhaustive search. For every particular channel quality pair, you could search over all possible in the capacity space. This is a very dumb algorithm. I agree, nobody will do this, but let's just do this as a thought experiment. Try every possible user 1, user 2 pair, rate pair, modulation coding scheme pair. And if it succeeds, it's green, meaning the transmission succeeds with reliably, it's green, and otherwise it's red. So you do this for every possible point, and you trace out the boundary, and that's your capacity region for this particular channel state. For some other particular channel state, you do the same thing, you'll get a different region. This is a ridiculous exponential search, and essentially, even if you could search sort of every millisecond, you could search one point, even for a 4-user system, this search just blows up. But you don't want to do this, you want to do something smarter. And there are many obvious things you can do already. I'm sure many people in the audience can see that you can try to improve the speed. So what we want to do is 2 things. 1, dimensionality reduction, and 2, monotonicity. So let's talk about each one of these. The dimensionality reduction postulates, this is a hypothesis at this point, that if channel states are nearby, their capacity regions are essentially the same, because everything is quantized. It's not a continuum. The modulation coding schemes. So you should be able to cluster channel states and say that every channel state in a particular part of the state space should have exactly the same capacity region. And this is just a postulate. If this is indeed true, then you need to learn clusters and learn a map per cluster, which can hopefully you can do much better. The second is that the monotonicity, which is again obvious. Let's look at a particular capacity region and look at a particular direction. Okay, in the capacity region. Let's say that along this direction, this particular rate point succeeds. You know that, therefore, everything below should succeed as well along this direction. Because lower rates will succeed, we know from just the physical reality of wireless transmission. Similarly, if something fails, then everything above will fail. And this says that some efficient search procedure can be constructed noisy search procedure can be constructed to actually find this boundary with potentially low regret. Okay, so that's really the idea of the algorithm. You want to sort of search, you want to do joint clustering of this capacity region, and you want to do some efficient search to find the boundaries and create essentially a table which can be used by the scheduler, and we want to see what kind of performance you can get. Our theoretical results are on a bandit algorithm for doing this kind of efficiency, on doing this kind of joint clustering and search, and some regret bounds on it. But what I think is the more interesting part of this piece of this work is how well does this, what happens in a realistic system. So let's move forward. So I guess I have another 6 or 7 minutes left. Is that correct, Shrikant?
Yeah, sounds good.
Okay, thanks. So the algorithm overview is, I go very quickly through this. It's basically, for those of you who have played with bandits, is an epoch-greedy algorithm. An epoch-greedy algorithm essentially means epoch-greedy algorithm with experts means the following. You do some pure exploration of trying to learn these partitions at the capacity region. Then assume that whatever you learned is indeed the ground truth. Exploit for a while what you have learned, and then switch back to exploration. And if you tune the exploration and exploitation correctly, you should be able to get some regret guarantees. What is messy here is that this is not typical bandit type exploration. You're trying to learn various things. You're trying to learn how to partition the channel state space into clusters, and then trying to learn a capacity region for each one of them during this exploration. So I'll just talk about what an exploration means for this kind of an algorithm. Essentially, what you want to do is the following. Suppose you have a bunch of channel realizations. Okay? You want to create such a tree. This is in the user 1, user 2 channel state space. These blue points are all possible channel realizations. So over time, you're going to see these blue points. What you can see is that you pick a particular rate point. Okay, that means there's a particular modulation coding scheme for user 1 and user 2, and you see that certain points succeed and certain points do not succeed. Those are the red dots, and certain points are successful. This basically says that you can, if you have experts, which is a bunch of classifiers, you can potentially partition the state space noisily into 2 regions. Okay, so this partition, given this partition, now, so far you just have this partition. Now you try some other rate point. Okay, this particular rate point is such that it's inside the capacity region of all inside C1, C2, and C3. So what are the C1, C2, C3? Suppose that the ground truth is that the partition P1 is this region and its capacity region is this one. P2 is this region, its capacity region is something else. P3 is this region, which has a different capacity region. Okay? This blue point here is within the capacity region of all 3 things, so it's not going to separate P1, P2, or P3. Okay, so everything is going to succeed. Whatever channel state you try, you're not going to separate these partitions. When you try yet another 3rd point, well, this point can visually, it's clear, it separates C3 from C1 and C2, and so you'll get a different partition. So essentially, it's a tree classifier we are building from noisy data inside an explore phase, and on top and on the outside phase is basically an exploitation, and then you iterate between explore and exploit using bandit methods. So I don't want to get too much into detail because I want to spend at least 5 minutes talking about so what with all this stuff. What you can do with this, of course, is you can get some sort of usual regret guarantees, which is very similar to what you would get with the vanilla stochastic contextual bandit with experts. But I think the more interesting part of it is so that first, is there really clustering in the system? Question number 1. So the whole thing is the complexity reduction was postulated that there's actually clustering, low dimensional clustering in the system. And 2, if you do this, what are the best hand-tuned tables? Can you actually get improved performance or some sort of robustness? So the system we tried, so this is AT&T's internal 5G NR simulator system. It's basically bit precise stack. The only simulation aspect of this is the channel model itself, but everything else is standard. It's essentially standards compliant. I can go into the details of what this is, but maybe in a later discussion. But what we did is we modified the scheduling, the resource manager in that. Instead of sort of looking at a fixed table, we changed their system and put in a bandit algorithm for creating this modulation to coding scheme, MCS to CQI table. That's essentially, so it's a dynamic map that's basically in their system. And so what can we see from that? Well, first, if you look at in this plot, this is just a single base station with 4 users. What you can see, first of all, this is the signal to interference ratios of 2 users. You can see clustering. So all these orange dots roughly have this as the throughput region. All these blue dots, there's some noise here, of course, has a different throughput region trade-off. So it looks like you setting a small number of clusters actually makes sense. That's point number 1. So this basically says that the kind learning to cluster and then learning maps for each cluster is actually a meaningful problem. But beyond this, what are the performance implications of using an algorithm of this form? Okay. So I'll walk through a few different scenarios. So let's first start with a single cell system. Very, very small number of users. So there are different hand-tuned policies you can design. I'm sure you can imagine there are various considerations. How robust do you want to be? How many extreme scenarios do you want to handle, and so on. And a major carrier could have different policies in their system. So you can try a benchmark of 3 different. We created a benchmark of 3 different policies, internal policies, versus a learning-based algorithm. Let's look at sort of throughput. The x-axis is time and y-axis is throughput. Initially, the throughput per user is extremely poor with the learning-based algorithm, and it takes about order of 10 seconds. Which I remember the scheduling time scale is about 5 milliseconds. So it takes order of 10 seconds before it can learn anything meaningful. But once it learns something there, it is essentially matching the performance of the best of these 3 AT&T fixed schedulers, at least in this scenario. And in terms of probability of success, again, when you're deploying these things, you'd like to have a 90% probability of success. And you can I didn't talk about it, but you can modify the algorithm to ask for a success probability and so on. It is giving those kinds of success probabilities. So far, so good. Sorry. If you go to a different scenario, in this scenario, well, again, for about order of 10 seconds, you're worse, but then it's about 20 to 30% better. But what is more interesting, I think, is that as you go across scenarios, the best AT&T hand-tuned policy changes across these scenarios, whereas a learning-based one matches or outperforms the best of the 3 after a reasonable amount of time. And this observation seems to hold even when you sort of go to a multi-cell scenario. Of course, the caveat is only one of the base stations was using our algorithm. All the other neighboring base stations, the system was just using a static table. Okay, so there's no interaction of these tables. But given this caveat, again, you see similar types of things. The best scheduler, the best table is scenario specific, whereas a learning-based one meets the performance of the best one. And in some scenarios, for example, if something in an extreme scenario, you can actually outperform any of these sort of handcrafted ones quite a bit more. Of course, you could hopefully have created another handcrafted one which would have met this kind of performance all the way from the beginning, because after all, this just learned a feasible table, and you could have used this a new policy which could have given this kind of performance. So really, the point is, it's not that the performance has improved, it is doing scenario-specific optimization. That's really the takeaway with online learning. And I think that's going to be increasingly important, going back to our original story of heterogeneity. This scenario-specific optimization is increasingly important for, I think, in these kinds of networks. So this is the second piece I wanted to talk about, and I want to summarize these are just two simple examples. There are so many more interesting problems when you're going forward into future networks. For example, let's think of network operations. There's this beautiful problem, which is that in a city of the size of scale of Austin, a major carrier will have order of about 100 base station changes per week. That's roughly the scale. When I mean changes, it means either a software update or some piece of hardware has changed or something has failed and that needs to be updated and so on. Each time you do this, there are several hundred parameters that needs to be set. And the way it's done right now is to use sort of thumb rules as well as parameters that have worked well in the past for that scenario. Put it in. This could be a handover threshold, for example, handoff threshold for some power control thresholds, all these kinds of hand-tuned parameters. These are put in place, and then then somebody is monitoring this actively for a week or so, and maybe slightly tuning this. As networks become more dense, it's clearly there's scope for in each of these parameters to base things like what we are talking about, some online adaptation, learn, and set the parameters. So there is a lot of scope for doing these kinds of things. But to do these things, you need the network to fundamentally change. One, that you need to be able to get agents deployed very quickly. The software platform needs to change so that you can quickly introspect the network. You should know where the data is. And you should be able to query the data in a transparent manner. All these things which the internet actually solved, but which is still not there in the wireless network, in the 5G network. And second, you need to be able to trust these algorithms, because if something breaks, how do you make sure that these things are safe? This is very scary. If some parameter change completely leads to failures or multiple failures in the network, how do you guarantee these kind? How do you make sure that there are guardrails in these things? Both of which are important, and these are all essentially unsolved problems. But I think that's really where 6G is going. The interesting things in 6G, at least from my perspective, are. I'll stop at this point, and I'm happy to take questions. Thank you so much for attending this.
Great talk. Standy also says, great talk. I guess there is a question or two questions by Haitham in the Q&A. I'm going to read them out one at a time. The first question is puncturing part of the 5G standard, or did you propose it?
No. So when we wrote this paper, so puncturing was at that point just coming into the 3GP. It was a discussion item we saw. And that's we just chanced upon this, I think, in a discussion with one of our corporate colleagues. And we said, hey, this is interesting. This gives us a new modality. And we wrote this paper. Actually, that's the paper that got the Bennett Prize. And now, because it was just coming out when we actually worked it. So we didn't invent it. It was it was in the 3GPP.
So is it a standard now, or do you know?
I don't know whether it's now. I suspect it is, but I haven't checked.
Okay.
It was a proposal when we looked at it.
Okay. Another question that Haitham has is puncturing taking place for uplink or downlink or both? And how is the reliability of URLLC guaranteed in case of puncturing?
That's a very good question. What I'm doing is puncturing for downlink. This paper is about puncturing for downlink. There's uplink URLLC. It's a much harder problem. I know that some other people have worked on it. I don't, including Gustavo, not with, and many others. I have not worked on it, and I don't know the state of the art with uplink puncturing. The way that puncturing essentially reliability is guaranteed is essentially, you want to think of it as an extremely low rate, very highly coded, and that's essentially the way you're getting this high reliability.
Right.
You throw resources at it essentially.
Okay. So the next question is from William Santosa. What will be the achievable application data rate of URLLC using this scheduling algorithm? And will the eMBB performance be disrupted when URLLC traffic is scheduled?
Yeah, so the answer is that I don't know numbers of achievable data rate, but the kinds of things you're thinking about mental model is extremely low data rate mission critical applications, because it goes back to Haitam's question. You want to strongly code it because reliability is important. Okay, these are tiny packets. I would think it's order of tens of bytes to hundreds of bytes level. It's not bigger than that. So these are really tiny. And will eMBB performance be disrupted? It depends again on the load. So if you have URLLC traffic, which is taking 90% of the traffic, then there is no free lunch. Okay, but that's not what URLLC is designed for. It's designed for it is urgent and but uses a small fraction. So if it's order of 10%, yes, you lose 10% loss, but that's exactly what the kinds of schemes you have proposed. It makes sense in these settings.
I have a question. So in the second part of the talk, you talked about regret guarantees. The first part of the talk was the result asymptotic.
It's asymptotic. We don't have. So that's another really interesting question. What can you do with regret for those kinds of gradient controllers? I think that's a really cool problem. I think that's an important problem. I don't know if somebody has already solved it, but it's an interesting, at least in these settings, but it's an interesting problem.
So and also in the second part of the talk, you get better performance after an initial lag. So would that be an issue for deployment, or what did the AT&T paper say?
That is what AT&T care. They were really interested in what's the time scale. 10 seconds, is it reasonable? 20 seconds, is it reasonable? That's really what it comes down to go. So the next stage so we are working with them to do something else. The next stage of this project is you don't want to just cluster. So the problem is in the second part, the users are fixed. The users also actually need to change. So if you want to relearn for each user these clusters, it's a mess. So what you want to do is to jointly cluster users and the channels. And when a new user comes, you just slot it into saying this user looks like something else. And you can really speed up the learning there. Really the time, if you can do things within order of 30 seconds, then it's okay. If it's more than that, then it's hard. It's not clear that these learn tables will be that useful.
Okay. Thank you very much. Haitam says great talk. Thank you, Sanjay. So I echo that. And thank you again for accepting the invitation and giving a talk. See you everybody at the next colloquium series. Bye.